Hello good people and welcome back. So in this unit, which is unit 6, we'll be talking about interest rate. Why are we touching interest rate today in this unit? Well, we're doing that because so far we've talked about the various derivative instruments that are of interest to us. And we've said we talked about futures, we talked about forwards, we talked about options, and we're going to talk about swaps now. And one thing that's common to each one of these contract is the idea that at least for these first three, is the idea that the transaction is an agreement is entered into today. So an agreement is entered into today, but the actual transaction occurs at some point in the future. And so, of course, you understand that whenever the future is involved for us, we're going to have to consider time value of money. And so when we think of time value of money, we want to consider what are the payoff of each one of these contracts at expiration or maturity, and those payoff are going to have to be discounted to today's value in order to find to price those contracts. So understanding the behavior of interest rate over this period allows for us to assess what kind of discount rate it is that we will apply to the payoff that we obtain from this contract in order to value the contract. Alright, so we're going to talk about a couple of type of interest rate or rates. Treasury rates from government, the London interbank offered rate, that is LIBOR, that is from the British Bankers Association. We're also going to talk about the federal fund rates and the repo rate, among others. Now, treasury rates are instruments issued by government on its own currency, right? So you have a government, let's say the US government, and the US government issue bonds, and the bonds are issued in order to raise capital, and the promise rate on these bonds are usually what we refer to as treasury rates, and those are the return that the investors in government bonds or government securities earn on their investment. Now these are considered to be risk-free, right? They're considered to be risk-free, and the reason they're considered to be risk-free is simply because the government has a taxing authority, the government has a printing authority, and so on and so forth. Now, the second type of rate that we're going to look at is the London interbank offered rate, that's LIBOR. And what LIBOR is the rate at which two banks can borrow money from each other in an unsecured way. So Bank A can borrow money from Bank B, Bank B can borrow money from Bank A. And the fact that the exchange happens without any form of collateral makes it an unsecured loan, essentially, between the two banks. The LIBOR rate is established by is calculated by the British Bankers Association, and those rates are for loans of different maturities. So the maturities can range for 1 day to 12 months. So you can actually have a scenario where Bank A borrows from Bank B just for one night, and then the next day Bank A repays that loan. That is the 1 day maturity, or it can happen for a 12-month maturity. Now, the LIBOR rate is computed every day. It's calculated daily, and essentially what it is an average of the market rates, right? So what the British Bankers Association is going to do is going to ask several bankers to tell the British Bankers Association what are the rates at which they are willing to lend money and the rates at which they are willing to borrow money. And so they're going to be quoting each bank. So the first bank here is going to be quoting two rates. The second bank is going to be quoting the rate. The third bank is going to be quoting the rate, and so on and so forth. And all those banks have to have the same characteristic. That characteristic is that they have to be AA rated. So they have to have good credit rating. And the idea here is that by borrowing and exchanging with each other just for a 1 day or a 12-month, the probability of default, the chances that the banks are not going to meet their obligations are minimal. The probability of defaults are minimal, so they're fairly secured. And because that used to be the case, there were these the LIBOR rate was considered to be a risk-free rate, right, in the computation of derivatives value or the pricing of derivatives. Now we're going to talk about that a little later. Ultimately, what the British Bankers Association does with all of these quoted rates is computes an average, and that is the average that is now used by all the financial institution that borrow and lend money to each other. And also, remember, all of these institutions have to have a double A rating. Now, because these rates are quoted by banks, and the British Banking Association simply does compute an aggregate value for these quotes, these submissions by the major banks. Some people or some banks can essentially manipulate the LIBOR rate, right? So if they have to receive a payment that's going to be a function of LIBOR, they may be quoting high LIBOR rate for that day because they're expecting a payment that's going to be affected by LIBOR. So the LIBOR rate was heavily manipulated, and I think somebody got a 14-year prison sentence because of the manipulation of LIBOR rates. And those manipulations essentially led to a change in the valuation of some derivatives contracts, especially swaps, that used to use LIBOR as a proxy for the risk-free rate. Now they are going to be using another measure of interest rate, and that other measure of rate is what is referred to as the overnight index swap rate, and we'll talk about that also a little later. Now, there have been some suggestions that banks manipulated LIBOR, and they're not just suggestions. There was a prison sentence. There was somebody that went to jail for manipulating LIBOR for some time, and therefore LIBOR is not used anymore, or financial institutions moving away from using LIBOR itself as a proxy for the risk-free rate. Now, the federal fund rate, every organization has its own central bank, and the central bank is essentially the one that is quoting this US federal fund rate. And these are unsecured interbank overnight rate of interest. And what they do, and they're unsecured again, remember the idea that there's no collateral interbank, the idea that they are transactions that occurs between financial institutions, and they're typically overnight rate. They can extend to more than that, but they're typically overnight rate. They allow banks to adjust the cash balance or the cash reserve that they have with the Federal Reserve. So if you remember the discussion that we had with respect to margin at the exchange, and we remember the process of mark-to-market, where at the end of every day the margin gets adjusted, the margin accounts get adjusted to reflect the profit or the losses for each party. The same happens with the banks at the Federal Reserve in a sense, because the banks are required to keep at the Federal Reserve. So this is the Federal Reserve, and this is the first bank, Bank A, and that's Bank B. Bank A is required by the Federal Reserve to have a reserve requirement to be liquid, right? To be able to meet this obligation, they have to have a reserve requirement. They have a reserve requirement they have to meet, and Bank B has to have this reserve requirement they have to meet. At the end of every day, we look at the position of the bank, we look at the liability and the assets of the bank, and we see whether they need to add to their reserve, the capital requirement, or they need to subtract to their reserve. Let's say A needs to add to its reserve and B needs to subtract from its reserve, right? B doesn't need to have as much reserve with the Federal Reserve. B can subtract this much. So B has to subtract, but A has to add. Instead of B withdrawing from the Federal Reserve back to its own account, what B may be able to do is loan the extra money that it has available here to A for the period, for the night until the next day. And if the next day B needs until the next day, and the next day A is essentially paying B for that overnight loan, that makes it such that A doesn't have to inject another amount of money into that account with the Federal Reserve. That's the idea there, managing those cash reserves with the Federal Reserve at the end of every day. That's because of the mark-to-market. The assets and liabilities have to be reassessed at the end of every day, and the capital reserve or the cash reserve need to be adjusted. The federal fund rate is the rate at which the banks loan money to each other for the purpose of meeting those capital reserve requirements. Now, the effective fund rate is the average rate of the broker transaction. So these transactions happen with several banks, and what happens at the end of the day is we compute a weighted average based on the size of the transaction. So if this loan between A and B was, say, 10 million, and another loan between C and D was, say, 8 million, all of those transactions are weighted, and we compute a weighted average of those broker transactions, and that leads to what is referred to as the effective fund rate. Now, the central bank may intervene with its own actions to raise or lower the rate. The federal fund rate can be adjusted, can be increased or reduced, and there are many. This is what's happening in the U.S., but the Chinese central bank would do the same thing, and the Japanese central bank would do the same thing, the Korean central bank would do the same thing, and so on and so forth. All right, repo rates are repurchase agreement, and they are repurchase agreement in a way they are secured loans. That's what they are. And when we refer, let's just go ahead and read this. The repurchase agreement where a financial institution that owns security agrees to sell, this is the key word here, agrees to sell the security, right, today for an amount that's labeled here as X, and buy them back in the future for an amount that's slightly higher that's labeled as Y. So we have two banks, A and B, and they enter into a repo agreement. And the repo agreement says A has a security here that is going to sell to B at the price X, and at some point in the future, A is going to buy back the agreement, the contract, from B at the price as Y, where the price Y at which A is buying back is greater than the price X at which it's sold. So that difference gives what? It gives that Y. So Y is simply going to be equal to the future value of X, right? Because Y is paid sometime in the future. X is the price that A sold the asset to B at. And so A received X today, and A has to pay back Y in order to receive the asset back. So Y is nothing else but the future value of X. And so if we did that, we would say that Y is going to be equal to X multiplied by 1 plus an interest rate here for a given period of time. That's how we do the future value, right? In discrete time at least. And so this rate at which the Y is computed here is what we refer to as the repo rate. So this would be our repo rate. That is, in a way, A, by selling the asset, is borrowing X and has to repay Y at an interest that is the repo rate. Now, the financial institution obtained the loans in effect, so by selling and guaranteeing that future repurchase, it is essentially borrowing and putting that security as a collateral. The interest rate is calculated from the difference between X and Y, and is known to be the repo rate. So the difference is that repo rate is the growth rate of X to become Y over that period of time, and that's our repo rate there. Now, just like what we described with respect to LIBOR rates, repo rates can be overnight. Actually, they're generally mostly overnight rate, and they are referred to as overnight repos. But you could also have long-term repos. The idea is to have a series of rollover short-term repos, and those are referred to as term repos. Now, the term repos are long-term, whereas overnight, of course, are short-term overnight repos. Now, you remember our discussions of swap, where we said that, and that's in, I think, unit 1 or 2, where we said that a swap is nothing else but an agreement or an exchange, and it is an exchange of a floating rate, as was a floating rate, for a fixed rate. Right, so you have variable payments that have to be made, or you have but somehow you prefer fixed payments versus variable payments. The swap rate is going to be the fixed component of this arrangement, where the floating rate was typically, the LIBOR was typically used for that floating rate in swap agreements here. So, and that is what we refer to as the most common swap, is where the LIBOR, which is a floating rate. Remember, the London Bankers Association or the British Bankers Association is the institution that computes these rates for us, the LIBOR rates, and they are floating because they're computed every day at the end of every day. And that rate is exchanged for a fixed rate. The fixed rate here is what we refer to as a swap, and the LIBOR rate will be the floating rate. A swap rate where the 3 months LIBOR is exchanged for a fixed rate has the same risk as a series of continually refreshed 3 months loan to a AAA rated bank. So again, the idea here is that it is less riskier to roll over a series of 3 months loan rather than engaging in a long-term loan. And so that's what we're saying here when we say that the swap rate where the 3 months LIBOR is exchanged for a fixed rate, for that fixed rate, which is that swap rate that we have, has the same risk as a continuously refreshed 3 months loan. That's a 3 months loan that is updated every period. Remember, the swap usually in the sense here, what we have here is we have two options. We could either make a 5 year, so let's say 3 options. Here we can make a 5 year. We can make, let's say this period here is 5 years. We have Bank A here and Bank B. Bank A can make a loan to Bank B that has to be repaid in 5 years, right? That's the 5-year agreement. So let's say the loan is 10 million. So Bank A makes a loan of 10 million to Bank B today for 10 million. Loan has to be repaid in 5 years. Because it's a 5-year loan, the risk is high because Bank B might default in 2 years, right? Or in 3 years. The alternative is for Bank A to say, well, we're not going to give you a loan of 10 million right away. What we're going to do is we're going to give you a series of short-term loans. So it's going to be a loan of 1 million, 1 million, 1 million, 1 million. Or they say, because this is 5 years, so they say 2 millions every year, and 2 millions every year for 5 years. That's going to make it 10 millions, right? Now, because they're short-term loans, so the 2 millions here that we're making, the 2 million loan that we're making today is going to be repaid in a year. The next 2 million that you're getting is going to be repaid in a year, and so on and so forth. So that's the rollover, the continually refreshed 3 months loan, the short-term loans. An alternative, it would be getting into a swap rate, 3 month swap rate LIBOR, where you're doing essentially the same thing as we're doing here, but that exchange happens every 3 months. And that's why we say here that these two last options, entering into a swap agreement or making that continually refreshing 3 months loan, are equally risky, but ultimately these two options are less risky than the 5-year option. Next we have the OIS rate, and OIS rate refers to an overnight index swap, and this is essentially what we are going to use now to value options and to value derivative instrument. They used to be LIBOR was looked at as the risk-free rate, and it was looked at risk-free rate LIBOR, that is, because it involved double A rated bank, right? So it involved those banks that were not likely to default in the short term. And say 3 months was relatively short. The probability of default of a bank in the short term was pretty low. That has not been the case as demonstrated by the financial crisis that we observed in 2008. And so the LIBOR, and also with respect to the manipulation that we talked about earlier by some of the financial institution and manipulating LIBOR, we realized that LIBOR is not quite risk-free as we thought. So the overnight index swap is now what is going to be used, and that is a swap where fixed rate for a period, that's generally a period of 3 months, is exchanged for, this time, the geometric average of the overnight rate, right? So we're using a geometric average of an overnight rate, and that is what we're going to be using as a variable rate, and the opposite side is going to be the fixed rate. So it used to be, remember, that LIBOR was that variable rate, and now it's going to be the geometric average of the overnight rate. Now this can happen for maturities up to 1 year, and there's a single exchange that's going to occur within that 1 year. Now, for maturities beyond the 1 year, there are periodic exchanges, so every quarter or every month, and so on and so forth. Ultimately, the OIS rate, the OIS rate, remember, it's overnight index swap rate, is a continuous refresh overnight rate as well. Remember, it is the geometric average of the overnight rates. We also remember that the overnight rates are essentially the federal fund rate, right? Because we talked about federal fund rate, and that's the rate at which the banks loan to each other. Typically, that's what we refer to as the overnight rate. All right, so let's talk a little bit more about this idea of using risk-free, of using LIBOR as risk-free versus using the treasury rate as risk-free. Well, it turns out that the treasury rate I consider to be artificially low. And the reason the treasury rate are artificially low is because there are incentives that are attached with this treasury rate in order to attract investors, right? And so one of those incentives is the fact that banks are not required to keep capital for treasury instrument, and so there is no capital requirement for treasury instrument. That is an incentive for banks to hold treasury instrument. It doesn't mean that there is no risk that's associated. Well, now in the earlier slide, I mentioned the fact that we used LIBOR. I think I was here. We used LIBOR as a proxy of interest rate, of risk-free rate, because LIBOR is the rate at which these two banks essentially loan and borrow money from each other, and they are essentially double A rated bank, which means they have a good credit, so the probability of them defaulting within a day is fairly small. Now, this was the case, but that has changed so far. And the reason LIBOR was used then anyway, before and not the treasury rate, which are considered default free, is because the treasury rate assumed to be artificially low. And while they are artificially, not assumed, they consider to be artificially low because the government offers additional incentive to attract investors into investing with treasury securities. And so, for example, banks are not required to keep capital for treasury instruments, right? So the savings in capital, or the value of that savings, should be accounted for and it is not. And treasury instruments are also given favorable tax treatment, so there is no taxes on the profit made on an investment in treasury instruments in the US at least. And so the tax advantage or the tax benefit there that's offered by the government is not accounted for in the valuation of that treasury rate, and therefore that treasury rate is considered to be artificially low. Another way of thinking about it is when you're investing in treasury, you promise what we label as risk free. However, that tax savings, right, should be added to that, so that the value of the tax saving for a private investor or retail investor, or the value of this capital requirement that doesn't have to be met by the banks, also has to be added there. So by not considering the value of this tax requirement, we are essentially deflating this risk-free rate of return. That's why they are referred to, or they are considered to be artificially low. So instead of using the treasury rate, LIBOR used to be used, and then we observe those situations where bankers were taking advantage of manipulating LIBOR rates, and now we are working with IOS rate. And remember, when we talked about IOS rate, we said that they are essentially the fixed rate that are received in exchange for the geometric average of the overnight rate. Now, the overnight rates we said are the federal fund rate, right, or the effective federal fund rates. So the IOS rate, the OIS rate, I still say IOS, the OIS rate, overnight index swap rates, are now used as a proxy for the risk-free rate. Now, the way we're going to measure interest rate is by referring to its compounding frequency, and that's hugely important, because the compounding frequency dictates what the future value of the investment is going to be, or what the present value of the investment is going to be. It has a big impact. And so the compounding frequency used for an interest rate is going to be looked at as the unit of measurement of that interest rate. And that is very similar to looking at miles or kilometers when you're looking at other units of measurements. So what is the impact of compounding? Well, the impact of compounding is fairly straightforward, right? The higher the compounding period, frequency, the higher the future value. So basically, you remember from your previous courses in corporate finance that the future value is equal to the present value 1 plus the interest rate raised to the power of t. Now, this is assuming that the interest rate, it compounds for a unique period, right? So that is, say, for example, annually. In this case, the interest that you label here is going to be annual, and t here is going to be the number of years. Now, if the interest is compounded multiple times a year, we can adjust this formula by dividing the interest rate here by m, where m is the number of compounding period, and multiplying t by m as well. And so what we're going to have is, if t is going to be equal to 1, that's 1 year, the future value is going to be equal to the present value multiplied by 1 plus the interest rate divided by m raised to the power of m, right? Because t is 1, so 1 times m is m, that's why we have m here. And that is essentially what you have here, where a is the amount of money you have, that's our present value, 1 plus the interest rate that you quoted, that's the annual interest rate, divided by m, which is the number of compounding period within the year, that's r divided by m raised to the power of m for 1 year. That is, here t is equal to 1. So m, which is the number of compounding period, is going to be equal to 1 for annual compounding, is going to be equal to 2 for semi-annual compounding, 4 for quarterly compounding. That is, there are 2 semi-annual periods, there are 2 6-month period in the year. Here there are 4 3-month period in the year for quarterly. There are 12 1-month period in the year. For monthly, there are 52 weekly periods in the year, so there are 52 weeks in the year. and there are 365 weeks in a year. And typically this daily compounding is also looked at with respect to the number of trading days. So there are 252 trading days in a year. So there are 252 trading days in the year. Now, as we see the number of compounding period increases here, the future value of this investment also increases. As we tend to infinity, as the M can, so this compounding period hits daily, it can go to hourly, or it can go to minutes, or it can go to seconds. Right? So as you increase the number of compounding period, this future value here, so let's put it this way, this is going to be our future value, and this is going to be our number of compounding period. As you increase the number of compounding period further to the limit, the future value tends to increase at an exponential rate, right? So because that future value tends to increase at an exponential rate, we can express the future value, this expression, as follows. So we can go back to the board here. We can say that what we had as future value, which is equal to present value 1 plus the interest rate here divided by m raised to the power of t times m, that can be expressed as a function, as an exponential function of the present value. So it's going to be present value exponential of. Now what we're going to have is going to have a different interest rate. That's going to be a compounded interest rate multiplied by t, which is the period. That's t here. And the question that we want to answer now is, and again, here it is the same apply, right? So we would essentially do the compounded interest rate divided by m, but then we also going to have to multiply t times m. So the m cancel each other. What we can simply have is the compound interest rate multiplied by t. So the question is, this is going to be, this interest rate here is going to be the quoted interest rate. That's what you're told. The equivalent that accounts for compounding here, or the continuously compounded interest rate, is going to be this value here. So how do you go from this interest rate, which is the interest rate compounded for m periods within the year, to that value? So how do you convert those two? Well, in order to do that, you would essentially set those two this equation to be equal to that one. So you can simplify the present value. The present value can cancel each other. What you're going to have is 1 plus the interest rate that you have. Let's call that Rm, right? The interest rate that will need to be compounded over a period of time. That's the one that's quoted, divided by m raised to the power of t times m. That's going to be equal to the exponential of the continuously compounded interest rate multiplied by t. Now, the way we're going to solve this, and again, what are we looking for? We're trying to find what that continuously compounded interest rate is going to be. Well, our continuously compounded interest rate is going to be equal to, we're going to take the log of this, and we're going to take the log of that, right? So when we take the log of each one of them, we're essentially getting rid of the exponential. And by doing that, what are we going to have? We're going to have t times m log of 1 plus the interest rate divided by m. That's going to be equal to the real continuous compounded interest rate multiplied by t. And then now what we're going to do is just simplify the t here, and our continuously compounded interest rate is going to be equal to the log of 1 plus to m, that's m here, times the log of 1 plus the quoted interest rate divided by m. And that's what we have for our continuously compounded interest rate. That's the value that we're going to be using, and we're going to use this quite a bit. Now, let's say we're given the continuously compounded interest rate, and we are asked to find the equivalent rate that will be compounded for this number of period, m period. And so if we were to do that, we would simply solve again for this value. And the way we're going to do that is going to be the same approach, right? So we're going to say, we're going to go from here, and we're going to say the continuously compounded interest rate divided by m is going to be equal to the log of 1 plus that interest rate we are interested in, that's our quoted interest rate, divided by m. That's what we're going to have. Now, in order to get rid of the log, we're going to take the exponential of it. So it's going to be the exponential of continuously compounded divided by m is going to be equal to 1 plus the interest that we are after divided by m. And so to solve that even further, what we're going to have is the exponential of our continuously compounded interest rate divided by m minus 1 is going to be equal to that interest that we are interested in divided by m quoted annually. So the interest that we are looking for is going to be equal to the exponential of our continuously compounded interest rate, as our c here, divided by m minus 1, and then we're going to multiply that by m, and so this is what we're going to have. So overall, the two equations that we were after are going to be how do we find our continuously compounded interest rate. Our continuously compounded interest rate equation is what we have earlier. I'm going to shrink this to see if we can have, actually I don't need to rewrite this. Our continuously compounded interest rate is going to be equal to this value, whereas the equivalent rate is going to be equal to that value here. Now, the continuously compounded interest rate is essentially that equivalent rate when the number of compounding periods tend to increases, right? So as the number of compounding period increases, this is the rate that we're going to be using. Now, when the number of compounding period is smaller, that is m is smaller, these two values tends to be about the same. They tend to be about equal to each other. All right, so let's go back to our slides here and look at it even further. In the limit, that is when the number of compounding period increases, as we compound more and more frequently, the number of compounding period increases, we obtain a continuously compounded interest rate. And so that continuously compounded interest rate says that $100 is going to grow at the rate of 100 multiplied by the exponential of that continuously compounded interest rate, which is r here multiplied by t. And we showed that if we go back to the board, we showed that it is the same as saying present value multiplied by the exponential of the continuously compounded interest divided by m multiplied by t times m, right? That's the same as that. R by m, t times m. The trick here though is that the m cancel each other, so we really don't have to leave the m's there, the number of compounding period there. So this cancel that one, and we are left with this multiplied by that. That's why we have this here. All right. So the $100 is gonna grow to $100 multiplied by the exponential of RT when invested at the continuously compounded rate R for a period of time T. And so if we were to do the opposite, if we were to find the present value, what would we do? Well, if we are to find the present value, remember from here what we're saying is that the future value is equal to the present value multiplied by the exponential of the continuously compounded interest rate multiplied by t. So the present value is going to be equal to the future value divided by the exponential of the continuously compounded interest rate multiplied by t. So we can rearrange this, so it's going to be equal to the present value the present value is going to be equal to the future value multiplied by the exponential of, this time we're going to do continuously compounded interest rate, that's RC, multiplied by t, but then this time because we are moving this up, what we're going to do is we're going to attach to it a negative sign here, right? So we're going to have the negative sign here. So the negative sign for me here says we're using a present value factor. The positive sign here says we're using a future value factor. So our present value is going to be equal to whatever future value we get multiplied by the exponential of our continuously compounded interest rate multiplied by t. So whenever you have the negative sign, we're working with the present value. Whenever you have a positive sign, we're working with the future value. So we go back here, and so our present value, at least if we are receiving 100 in the future, that is at time t, and we're discounting it at the continuously compounded interest rate r, the present value is going to be that future value, which is 100 that we're receiving at time t, multiplied by the present value factor, that is exponential of minus rt at time 0. And again, in this case, we are saying that the interest rate is continuously compounded. That is, the frequency, compounding frequency shrinks. And typically, that's what we're going to assume in finance. So the conversion formulas are the ones that we just derived, right? We said that RC is our continuously compounded interest rate, and RM is the same rate with compounding M times per year. So the way we find this value, RC and RM, is essentially by saying, well, the formula that you've been using all along that says that future value is equal to present value multiplied by 1 plus Rm divided by m raised to the power of t times m, that is equal to the same expression that's going to be present value, but this time we're going to use continuously compounded. That's the exponential of. If we use continuously compounded, we're going to use a continuously compounded interest rate. That's going to be RC multiplied by t. Now remember, we can do RC divided by m as well. That's going to be continuously compounded rate divided by m multiplied by t times m. The trick here is m cancel each other. We are left with RC times m times t. That's RC times t. That's what we have. So if we set this and then we try to solve for this is what we get, right? And we try to solve for this, what we're going to get is this one. And that's what we did on the board here when we set this to be true, and then we went from there to take the log of each side. That is, the log allow for us to be able to get rid of the exponential term. That's why the exponential term is not here anymore. And so the log also took the t times m down, and we solve for the continuously compounded interest rate that we have here. And so once we had our continuously compounded interest rate, we could now find the equivalent rate to be compounded for m period, and that will be the Rm. That's what we obtained. And so our continuously compounded interest rate that we found was essentially equal to, I'm going to use a different color here just to highlight that a little better, was equal to this value that we have here. That is the number of compounding period multiplied by the log of 1 plus that interest rate that we ought to be compounding for m period divided by m. And the equivalent rate is going to be equal to the exponential of the continuously compounded interest rate divided by m this time minus 1 multiplied by m. And that's essentially what we have here in that. Alright, let's look at a quick example of this. In our example, what we're going to have is going to be the following. Let's say we have a 10% with a semi-annual coupon compounding is equivalent to, the 10% semi-annual compounding is equivalent to 2, because the semi-annual, remember what our formula is. Our formula is m multiplied by the log of 1 plus our interest rate, which is 10% r divided by m, right? Also our m divided by m. And so that would be our m here would be the 10%. What we're going to have is, and semi-annual means m is going to be equal to 2. So we're going to have 2 multiplied by the log of 1 plus 10% divided by 2. That gives 2 log of 1 plus 5%. That is 2 log of 1.05. And that's essentially what we have here. That's going to give us a value. If we go pull our financial calculator, I'm going to say 1.05, we press the log as the ln, that gives us that, and we multiply that by 2. And that gives us 0.975, that's about 9.758%. So it gives us 9.758%. And this would be our continuously compounded interest rate. So if we have a 10% generally quoted rate that compounds semi-annually, the equivalent continuously compounded rate would be 9.758%. Now 8% with continuously compounded is equivalent to 4 times the 8%, the exponential of the 8% divided by 4 minus 1, and that's about 8.08% with quarterly compounding. So in this case, what do we have? We have m is equal to 4 because we are working with quarterly compounding. And so Rm is going to be equal to m, the exponential of m multiplied by the exponential of the continuously compounded rate divided by m minus 1, right? And so what do we have? M is equal to 4 multiplied by the exponential of our continuously compounded rate here is 8%, so it's 8% divided by 4 minus 1. And so let's pull our financial calculator and do just that. So we have 8%, so that's 8%. We divide that by 4, divided by 4, that should give us about 2%. We take the exponential of that as second function, log, that's the exponential of that, minus 1 equals, that gives us that, and we multiply by 4. And that gives us about 8.08%, and that's the 8.08% that we have here. Now, the rates used in option pricing are usually expressed in continuously compounding, expressed with continuously compounding, and so typically we're going to be assuming that what we have is essentially this expression. So it's going to be, this is RC, and that is what we will be working with from now on. So now we know how it is that we measure our interest rate essentially, and we said that the number of compounding period is critically important in that estimation of the continuously compounded interest rate. But at the end of the day, in our valuation, if you remember the discussion that we had early on, when we said that the transaction occur at some point in the future, and the reason why we're even looking at this interest rate unit here is because we're going to have to estimate what it is discount rate that we're going to apply in order to find the present value of the outcome of the contract that we have in front of us. And that rate that we have to apply, which is going to be assumed to be a constant rate over a period of time that matches the maturity of the contract, is what we're going to refer to as a zero rate. And so the zero rate, often called also as a spot rate for a maturity of time t, is going to be the rate of interest earned on an investment that provides a payoff only at time t. What does that mean? It means that we enter into the contract today, the payoff happens at time t, nothing happens between now and time t. So nothing happens between this period. So that zero rate is going to be the constant rate that is going to be used to find the present value of this payoff. So if we're working with a call option, the payoff may be the maximum of the stock price minus the strike price and 0. We're going to get that payoff, and then we're going to find the present value of that payoff in a sense. That's the idea that we are trying to infer here with a zero coupon rate, a zero rate. If you're working with a bond would have an initial outflow here. It was going to have a maturity there, but between these periods we're going to be working with coupon payments. And so the difference between the zero rate and the return that you earn on a bond is that no cash flows is accounted for this period, right? Very similar to that of a zero coupon bond, if you will. All the cash flows here have a coupon rate equal to 0. And we'll see how that applies next. But before we do that, we're going to refresh our memory on how bond pricing works and how we can find the yield to maturity on a bond. And we're going to build on that intuition with the pricing of bonds, coupon paying bonds and zero coupon bonds, in order to infer what the appropriate zero rate should be for any given contract. Now, I will see you in the next video for just that. I'm going to stop here, wrap this up for now, and when we get back in the next video, we're going to wrap up this unit. I'll see you next video.